Hi there! Because the APS March meeting was cancelled, I decided to record my talk. It was supposed to be in session B44, talk number 5. And it's about recent advances in the development of the Octopus code for GPUs. My name is Sebastian Ohlmann. I'm working at MPCDF, which is the Max Planck Computing Data Facility in Garching near Munich in Germany. You can see my email address here in case you have any questions. Feel free to drop me an email. Okay, so let's start with the presentation. So in this talk I would like to highlight the work we did in the last month in porting more of the Octopus code to GPUs. And this is work that was done in collaboration with several researchers at the Max Planck Institute for Structural Dynamics of Matter in Hamburg, namely Heiko Appel, Martin Lüthers, Michael Oliveira, and Nicolas Donconet-Deschamps. And so now the first question is, why at all GPU development? And there, if you look at what happened for CPUs in the last years, you could see that the performance increase was really slowing down. And this has several reasons, but the main point is it is like that, and in order to cope with it, you can look at GPUs which have a higher power efficiency, which means you can get more flops per watt. And if you go to larger and larger machines, this is essential. And you can see this if you look at, for example, the top 500 list of the fastest supercomputers. Also, if you look at the exascale machines that are planned to be built in the US, all three of them will have GPUs, and they will have the main portion of their computing power will be in GPUs. And so I think it's important to prepare now to be able to use those machines and get computing time in sizable fractions in order to do simulations. And that's why we are working on it. And so we work on the Octopus code. What is Octopus? Octopus is a density functional theory code with pseudopotentials. It uses a real space grid and finite differences to discretize the derivative operators such as the Laplacian. And it's mostly used for real-time, time-dependent calculations, also including external fields like a laser field or whatever. And it also includes lots of different options and algorithms. It's mainly written in Fortran plus some C, and it's open source, so you can find it at octopus-code.org and can download it and use it. The GPU version of Octopus was developed maybe 6 years ago or so. It is written in OpenCL, there's a wrapper for CUDA, and nowadays we mostly used the CUDA wrapper. It's used in an interface from Fortran to C, and it uses the driver API of CUDA, and then kernels are compiled during runtime. And in this way you can kind of more or less easily use it from Fortran as well. And then we have several basic code where we then have the kernels running on the GPU. Okay, so all the benchmarks I will show you have been done for this example system. It's a silver tip over a silver crystal that you can see on the right hand side. It's periodic in X and Y, it's not periodic in in the C direction. It consists of 312 silver atoms, and all in all it's 3,200 orbitals, and each orbital has 2.4 million grid points. And what I did is I ran different time-dependent runs for a converged ground state and then compared the timings for those. I actually ran those on two different benchmark clusters. One is called Cobra, it's at MPCDF. It has some CPU and some GPU nodes. The CPU nodes have 40 cores per node, so 2 20-core sockets. And GPU nodes is like a CPU node, but it also includes 2 NVIDIA Volta 100 GPUs, and interconnect is an omnipath. And then there's also a GPU machine at MPSD, so the Max Planck Institute for Structural Dynamics of Matter, and it has 2 8-core sockets, but 8 NVIDIA V100 with NVLink, so the GPU-GPU communication is very fast. So first of all, let's look at benchmarks in Cobra. And here I show you a comparison between a CPU and a GPU run. What you see on the y-axis is the time per time step in seconds, and on the x-axis the number of nodes. And as you can see, both scale quite well up to a certain point. But more important, here on the left hand side you see that the difference between those versions is more than 4x, so it means that the GPU version is more than 4 times faster than the CPU version, sorry. And if you look at the total cost of ownership of these Cobra nodes, then a GPU node costs roughly 2.8 of a CPU node, including the cost of buying them and also the electricity. And this means that right now it's cost efficient to run a GPU. So if you ask yourself, should I buy a cluster with GPUs or not, then actually for this kind of simulations, it's already worth. And just to give you some numbers here, so if you look at the point with 32 nodes, it's already using 64 volts, so GPUs, and the run on 64 CPU nodes uses 2,560 cores. Just to give some numbers. If you look at the scaling, so this is the speed up, which means it's the time compared to the time at 4 nodes. You see that the scaling of the CPU version is better than for the GPU version, but still it's not too bad. So at 60 nodes, the efficiency is still around 70% or so, and then it just gets worse here. So the green is ideal scaling, and then you see that the curve goes down a bit. Okay, so after showing some results that show you that it's already in a state where it can be used efficiently on GPUs, I'd like to mention some details on the implementation. So there are several points that we used, or several technologies that we used in order to speed up the code. And I just want to highlight a few. So just mentioning, we used pinned memory, which improves the transfer speeds. And that's because otherwise, if you don't use pinned memory but pageable memory, an extra operation needs to be done when copying, and this reduces the transfer speed. Then the next point is using streams, which is very useful to have asynchronous operations, so to be able to overlap things. Then we also use CUDA-aware MPI to enable GPU-GPU communication, and also some prefetching of data in order to overlap the communication from the CPU to the GPU, and also computation. Okay, so but before I go into details there, I'd like to show you how the data layout looks like in Octopus. So we have, as I already mentioned, a real space grid for the finite difference operators. And as you can see here on the right hand side, the grids can be quite complicated. So they can have a complicated shape for each molecules. And this means that we cannot simply have a 3D array, but we need to have some kind of more complex structure. So what we do is that we map this 3D grid to a 1D array, and the mapping is done in such a way as shown here on the right hand side. So these figures are, by the way, from this publication mentioned down here. And as you see here, for the example of a 2D array, the mapping to 1D is done in a cache-aware way. So we have these small parallel epibets, and when we go through it as indicated by the arrows, then the finite differences will reuse values from the cache, and this will speed up the calculations. And then the 1D array is looking like this. So if in 2D we have the interior and boundary cells, so we always have boundary cells on the outside, but also if we split the domain and parallelize over the domain, we will have ghost cells where we have replicated the values from the neighboring processes. And then the 1D array contains in the first part only the interior cells, and then in the second part the boundary cells. Okay, now if we use CUDA-aware MPI, I'd like to just briefly show why this is beneficial. So the timeline I show here is what happened before we implemented CUDA-aware MPI. This is when we have a distributed mesh. So first of all, we need to gather the points from the neighboring processes that we need in order to compute our finite difference stencil. Then we need to copy it to the CPU. What we then do is that we do the operation, for example, the Laplacian, first on the inner points that do not touch the boundary. Then we communicate these boundary points. We copy them to the GPU, and then we operate on the rest of the points that touch the boundary. Now this can be now improved by using CUDA-aware MPI. Namely, we can then directly use GPU to GPU communication to get rid of the copies. So you can get rid of the copies to the CPU and to the GPU and directly copy between GPUs. So then the timeline looks like this. We gather the points, we do the operation on the inner points, we communicate directly between GPU buffers. So this gather operation also takes place on the GPU, and then we operate on the rest of the points. And then if you combine this with streams, you can even overlap those operations on the inner points with the communication, and this gives an additional benefit in the time. Now some words about implementation. We get pointers to GPU memory from C, and then actually use CF pointer and Fortran to really get the Fortran pointer that we then pass to MPI, and this works very nicely. And just to give you an example of what this brings in terms of speed, on 8 GPUs with NVLinks on this machine at the MPSD, we get a peer-to-peer transfer speed of 24 gigabytes per second, which is very nice. So PCI Express is only around 12 or 13. And the speed up is roughly 2.4 versus using just a normal MPI. The second point I'd like to briefly show is prefetching batches. So we have several states that we have together in one batch, and if we cannot put all of them to the GPU because the memory is not large enough there, then we need to operate on one after the other. And this timeline here shows that we first copy to GPU, operate on it, copy back to CPU, and then the same for the second batch. But actually we can use prefetching in order to overlap those operations. This is shown here. So what we do then is, while we operate on the first batch, we copy the second one already to the GPU, and in this way we can overlap this. And even for the third, we copy it to the GPU while we still copy the first one back and while we operate on the second. And this all can be overlapped on those Volta GPUs because they have two copy engines. And so with this you can really save time. And for those time-dependent runs, you can see a speed up of roughly 1.8 in this one example, but the speed up is for the full run. And this of course speeds only up certain operations. And so with this I'd like to come to the summary already. I hope that I could show you that the Octopus code is now more efficient on GPUs than before, and we did quite some improvements based on different technologies such as pinned memory, streams, CUDA-aware MPI, prefetching patches, and also much more. And as a little outlook, what we plan to do next is to port more parts of the code because there's still some that do not run efficiently on the GPU, and also to improve the scaling still more. So I hope that you enjoyed the talk, and if you still have any questions or want to reach out, you can see my email address here, so feel free to contact me. Thank you very much.